Hi, in this video we're going to take a look at how to sketch a graph of a polynomial using calculus. Now before I get to an example, there's a couple of things I want to remind you that you know about polynomials. One thing you know about polynomials is that their domain is all real numbers. That means there won't be any holes, there won't be any vertical asymptotes. And then you may or may not also know that they don't have any horizontal asymptotes. And hopefully you learned that in pre-calculus. You should have seen that when you graphed polynomials in pre-calculus, they didn't have horizontal asymptotes. If you learned how to graph rational functions in pre-calculus, then you had to look for horizontal asymptotes. In fact, there's also no discontinuities of any kind. So with all of that information in mind, let's do an example. And as we do this example, I want to point out that I have not made up an example ahead of time. And I did that very intentionally. I'm looking at this as something you should be able to graph any polynomial using this technique. So let's try f of x equals 2x cubed minus 3x squared plus 5x minus 1. Is this something you could have graphed in pre-calculus? Yes, and it was a really long, complicated procedure. You had to find x-intercepts, y-intercepts. You had to find all the turning points, but you could only find those if they were on the x-axis. And if they weren't, then you just sort of sketched them in. Now we're going to find out where they really are. So the first thing we are going to look at is still the y-intercept. And I only look at the y-intercept because it's easy. F of 0 equals negative 1. See how easy that was? This is not really helpful in drawing our graph. It doesn't tell us anything about the shape of the graph, but it's a free point that was really easy to find. So we're going to use that. The x-intercept, in order to find the x-intercept, we're going to need to solve 0 equals 2x cubed minus 3x squared plus 5x minus 1. And this isn't a super easy thing to solve. And in fact, it's not easy at all to solve. So I'm going to just skip this. This is hard. Skip for now. All right, let's try to find critical points. So that's where f prime equals 0, or f prime does not exist. So f prime of x is going to be 6x squared minus 6x plus 5. Is that easy to solve? Let's see. Factoring, I need a product of 30 and a sum of negative 6. That's not easy. But this is quadratic, so we can use the quadratic formula. So that gives us x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's 6 plus or minus square root of 36 minus big number. What's that? Minus 120 over 12. 36 minus 120 is negative, which means that these are not real. So there are no critical points. There are no places where there's a horizontal tangent. There are no maxes and mins. Okay, let's move on and try finding inflection points. That means we'll need to look at the second derivative, f double prime of x. That's going to be 12x minus 6. If we set that equal to 0, we get x equals 1/2. And because we want an inflection point, we're going to actually plug in that 1/2, f of 1/2. That's going to be 2 times 1/2 to the third power minus 3 times 1/2 squared plus 5 times 1/2 minus 1. that's 2 times 1/8, that's 1/4, minus 3/4, plus 5/2, minus 1. That's negative 2/4, that's negative 1/2, plus 5/2, that's 4/2, that's 2 minus 1 is 1. So we have an inflection point at 1/2, 1. And there's only one inflection point because this is the only place where we had that derivative equal to 0, or that second derivative equal to 0. So what do we have? We have a little bit of information. Now that's not enough information to do this, but I'm going to start drawing the graph to see what we can get. So as we start drawing this graph, first of all, remember you're drawing a graph, label the axes, label the scale on those axes. And now we're plotting that point that we have for the inflection point, 1/2, 1, right there. And our y-intercept that we found earlier, that's down here at 0, -1. So we've got those 2 points. Now we don't know where it's concave up and where it's concave down. Is it coming down like this or is it coming down like that? So we're going to find some intervals of concavity. And so that means we're looking at this first interval, that's where x could be from -infinity to positive 1/2. And then the second interval will be from 1/2 to infinity. And we're looking just at concavity so that we only care about f double prime. So looking in here, if I have something negative and it's more negative than 1/2, so maybe 0, let's see, this will be negative. This should be concave down. And here, we're greater than 1/2, so that's going to be positive, and it's going to be bigger than 6, -6, that'll be positive, this will be concave up. So we know that it's going to be concave up here, concave down there, switches here, goes through that point, and the graph looks something like this. Now you'll notice I didn't bother to find the intervals of increase and decrease. The reason I didn't bother? Because we knew that it never changes. So it's either a strictly increasing graph or a strictly decreasing graph. And we knew these 2 points, so therefore it had to be increasing. There was no other way this could happen. So this is really all the information we needed. Now we could refine this graph by going back and saying, okay, let's figure out where this x-intercept is. Clearly there is one x-intercept, and we could find that one x-intercept a couple of different ways. One way would be to use factoring. I have no desire to factor that. You're using the P and Q method if there's a rational factor, and hopefully there is. If there isn't, then you can use Descartes' rule of signs, you can use intermediate value theorem, you can use all kinds of things to try and track down that x-intercept there. But we have a pretty good idea where it is. It's clearly somewhere between 0 and 1/2. So if you are using the P and Q method, you know to only check things between 0 and 1/2. If you are using Descartes' rule of signs, or if you are using the intermediate value theorem, you could use that to prove that there's something between 0 and 1/2, and then maybe is it between 0 and 1/4, and you could certainly play those games if you wanted to refine this graph, but this is really good enough. So that's it for now. Have fun drawing some graphs on your own.